Okay. So we're going to walk through this hypothetical internal erosion caused failure of Thunder Hollow Dam. So I'll walk you through the relevant information. Some of it will give you an brief overview, and then some of it will come more relevant as we go, and we can kind of try to reiterate that. But I'll just read this for you. So prior to calculating life loss, you must have the following information available. This has been done for you. So select the hydraulic breach scenario. So we're going to have the depth and velocity grid come up here in a little bit and get results from the hydraulic model of a breach scenario. So again, we'll have those grids. Prepare a geographic census data or populated structure inventory. So we'll have the population at risk number for you, and it's just one number by a few different regions. Select information from the EMA capabilities and planning, and we'll see how that comes into play. And it's a good idea to also look for information about the history of flooding in the area context. So this is like if you're actually doing it, it's helpful to know like, hey, this community has been flooded before. This was their evacuation rates, or this is the problems that came up. And it's a fictional dam, and you'll only have available what's on the slide/workbook. So it's all units in feet and feet per second for velocity. All right, so this is again, that kind of multi-step process for estimating consequences in general. Overlay the population, look at your hydraulic scenario and how that correlates with the warning that's likely to come out. Calculate the time available to actually complete the warnings, determine the population left behind based on those warnings and the rate at which people choose to evacuate or are able to evacuate. And then determine, given the depths and velocities we're seeing, what survivability are they likely to have, and then apply the fatality rate based on the fatality zone that they're in. So again, we'll go through all those steps one by one. All right, so here's the failure mode. Thunder Hollow Dam has had a minor seepage noted along the right abutment. The moderate rain event fills the dam to the spillway crest, top vector storage, which isn't enough to trigger inspection. Inflow matches outflow, keeping the pool level for a few days. Seepage is flowing and is monitored by a seepage weir and an automated recorder. The seepage rate triggers an alarm in the afternoon. The district sends an engineer to inspect the dam, who finds turbid water in the seepage channels. More staff arrive to consult on the dam condition. The muddy flow has noticeable increase at about 6:45 p.m. and continues to increase until seepage is seen on the dam face, which begins to ravel at about 10:45 p.m. Soon the downstream slope begins to slough and removing much of the downstream toe and right abutment. A little before midnight, a whirlpool is seen in the reservoir, followed shortly by a settlement of the crest below the pool level and breach at midnight. So again, we'll walk through all that a little bit. So muddy flow triggers the district EAP, and initial contact is made with the local emergency manager, who's made aware of the evolving incident. Intervention is attempted, but materials are being washed away faster than can be placed. When is there enough information to alert the emergency manager of the imminent breach? So this is our first, we'll come back to that in a second, actually. We probably should move these around. Estimate population at risk. So we're about to have a dam failure. How many people will be flooded? So inventory is brought in. You can see all these dots on rooftops. You sum up all those population in each of those structures to these different ranges. This isn't how we literally do it, but for simplified exercise we are. So the 0 to 1 mile range, right below Thunder Hollow, 900 people. This 1 to 3 mile range, from Rumbling Springs, is a little more than 20,000 people, and then more than 65,000 people in this bigger range down here. So you're given that information, don't even have to work for it. Here's another view of that, just so you can kind of see satellite versus street view, how people are structured, where evacuation routes are and stuff. Not that you'll literally be modeling it in this case. All right, so this is where that whole timeline of when muddy water is observed becomes more relevant. So we want to know when is warning being issued, and ultimately how many people are able to be evacuated. So at some point, the embankment's going to collapse. We know that even if the engineers of the dam do not know that yet. So we want to know when is threat detected and notification starts being received. Could be there, could be here. What do you think? So seepage begins to flow through a flaw and exit the downstream face of the dam. It is eventually picked up by a seepage flow alarm, triggering a visit by the resident engineer. So this is re-saying what we saw in the last one. Which observation would be sufficient to trigger an imminent breach notification? So after an engineer decides to notify the evacuating authority of the imminent breach, assume there's no hazard communication delay. So let's first, you all need to decide the likelihood that warning would be, our evacuation advisor maybe would be conveyed to the sheriff around this point, where muddy flow increases, or at this point, where slow gravel increases. This is going to be your opinion. You get to decide, and this will determine how the rest of the consequences goes for your exercise. No wrong answer here. We're kind of predicting based on this fictional example when warning will go out. So go ahead, choose A or B in your worksheet. And when still wrestling with what our fictional engineers would do. All right, so after the engineer decides to notify the evacuating authority of the imminent breach, assume there is no hazard communication delay and the sheriff is moderately prepared to issue an evacuation. The entire HAR will receive the same warning. So there is no hazard communication. We break this into a couple different pieces, like how long does the internal core communication delay take versus how long does the sheriff's communication delay break. For our purposes though, hey, there's a little bit of delay in this whole process. We think this is the most likely time. So given that, given what you chose A and B, and this most likely time over here, at what clock hour is the warning going to be issued? That's the second question here for your worksheet. Anyone confused by that prompt? Starting to see pins go down. We're not done yet. We still have a second here too. Okay. Cool. Assuming you've done that math just in these times, how much time is there between when the warning goes out and when this breach starts to occur at midnight? How many hours between what you just calculated in step 2 and midnight? All right, so in this sort of example, you can kind of think of this being ample warning and this being minimum warning. Again, these are simple sort of ranges. Anyone want to say what they got for the third step here? How much time are we looking at for A?
Yeah.
5 and 3. So 6:45. Okay. Yeah, sorry. So 5 hours from this, 6:45 plus let's say 15 comes out evenly to 7 hours. 5 hours to be 7 and midnight. If you chose B for minimum warning, that becomes 11 hours. Sorry, 10:45 plus 15 becomes 11 o'clock, an hour for average. All right, so calculate time available to evacuate. So we have, either what we say, 5 hours or 1 hour before the dam breaches. Once it breaches, the water doesn't reach max depth or cutting off evacuation all at the same moment, right? People immediately below the dam are going to get hit first, then them. So there's arrival time grids with different ranges. Hopefully this is more clear on your worksheets. And you can see like after breaches, they have a certain amount of time available. So if it took a day, that's not the right answer. That would be a day plus 5 hours or a day plus 1 hour of effective warning time. So for each of these 3 different impact areas, these downstream reaches, calculate the arrival time and then the time for evacuation. Now, obviously, you have to smooth it a little bit. Some of these people in these areas are getting different times. What do you think is the most likely or mode, median, whatever your situation preference is? All right. So this, at this point, becomes pretty subjective, right? I'm not gonna say there's a right answer for calculating what the average arrival time is. Unless you tell me, 5 days later or something like that, we'll say, well, that doesn't really meet the data. But anyone want to volunteer for the 0 to 1 breach rough time for evacuation? But 5 hours. 5 hours. So more or less instantaneously after breach, they're being inundated. And that's totally fair, right? I mean, you're in this 0 to half hour sort of range. So I mean, it's whether you want to say it's 5 hours or 5.5 hours, something like that, is what they're looking at, right? They have their only opportunity to evacuate is if breach is forecasted and they are told ahead of time to evacuate. That isn't always the case, right? Historically, some dams breach and no one at the dam is able to know that ahead of time. And you're only getting a warning if someone notices the breach or you're a little up more on the hill and you can see your neighbors getting flooded before you do. An environmental cue, but for this group, it's basically being driven by whether or not they get that ample or minimum warning. How about for the next breach? What are they looking at? 6 hours. So that's for the ample warning, I'm assuming. So yeah, they're more in this hour-ish range, perhaps. You know, again, probably a 0.5 to 1 is what I see most common. Again, code line aside, there's only a few people getting this more orangish color. That's reasonable. Yeah, I mean, again, I would say 5.5 to 6 hours or so. What about for the 3 to 5? Or sorry, that's miles downstream for the Southern City. Sorry, 9. So it's much more in this yellowish range, which is 2 to 4. So I'll have to, yeah, I'll probably take the middle or so and say, okay, 3 plus 5 or 3 plus 1, around there, is what you're looking at. So the further downstream, the more time they have to evacuate. All right. So how many people will be exposed to the flooding? So the next step is to estimate how many people are expected to evacuate in the time available. By combining the unknown warning diffusion and the unknown protective action initiation, we can derive a percent from the warned and mobilized curve. So this is basically telling you like, hey, we have some defaults called the unknown curves in LiveSim. We're using the unknown, which has a very wide range between the best case and worst case. We're combining those to get this combined warn and evacuation. And this is what you can use for this exercise. It's just extra funsy information. So you'll pull from that. And for this estimate, we can assume that people seek protective action initiation, they will evacuate safely. So we don't have to model all the blue cars going on roadways. As soon as they leave their door, they teleport to safety. So percent of the population remaining exposed can be calculated as 1 minus the initiating protective action. So you'll use this curve again for this exercise. And if you're saying, hey, I think 80% of people will be evacuated based on the time they have available to them, then the exposed percent would be 1 minus 0.8 or 20% left behind. So from this past exercise, you determine what you think time for evacuation is. Follow that curve, time after warning issuance hours to get your PAI rate. 1 minus that rate will give you your exposed. So then you can multiply your population by that number to get your exposed population. What do we think? Let's start with the 0 to 1. What do we think the PAI rate will be. So again, picking from this curve, we haven't done the 1 minus yet. They have, sorry, 80%. See, I honestly don't remember. So you're using ample, I assume. Warning. So that's 5 hours plus some change maybe. So we would go to the 5 hour mark, come up here. Yeah, 80%. If you're using ample, anyone use minimum? 30. So that was 1 and change is what you're assuming. So yeah, you come up here, pick 30, great, yeah. Oh, dang. Yeah. No, dang. Where's that? I'm the old guy now that doesn't. Yeah, okay. Hmm.
It'll show up.
Okay, little lag. All right. That's where I was, 1, 5. So you would take 1 minus that, 20 or 70% exposed. So what was the exposed population? People that did minimum? Sorry. Okay, I believe you. That sounds about right. And if it was minimum, how many were exposed? All right. So you can see right there, right, how important the warning issuance assumption would be to this dam, assuming there'll be consequences. So, you know, there's sufficient depths and stuff, which we'll get to. 180 versus 630, someone that's good at math, is that factor of 3, 4? So, I mean, that's a decent change in your risk, right? I mean, that's a half order of magnitude potentially shift, depending on how all this other stuff shakes out. So let's see how the other stuff shakes out. The 1 to 3, the rumbling springs, what the ample warning people get for PAI. 85 or so. Yeah, I mean, it kind of flatlines here, right? Like once you get a certain amount of warning, it flatlines ish. So we actually extend this out to 72 hours. So assume people have a lot of time, people that don't have cars, we're able to get buses to them and stuff. We'll drag this off screen. But you can kind of see there's diminishing returns to the warning issuance assumption. And eventually your uncertainty is going to be more driven by your PAI uncertainty. So it starts to become less of, hey, when did the people at the dam and the sheriff agree that there's a problem, and more of a, can you convince people that there's a problem and that if they don't leave, they could die. Sudden City for ample, a little bit more, we'll assume. Anyone want to say what the minimum was for these other 2 communities? Yeah. Sounds about right. Just a little bit higher than the 30, because they get another half hour or so. So what are our exposed populations for minimum and the rumbling springs? 13. And sorry, what the ample for rumbling springs? 3,700. 36. Wait. Okay, yeah. So still matters there. How about Sudden City exposed populations for ample? 9,800. 16,000. So matters less than it did for Thunder Hollow. All right. Flood severity and hazard zone. So again, this is the low hazard. People can walk through it pretty okay. High hazard, their structure is getting washed away. How do we get there? We look to our stability, our structural stability threshold. And this varies by your construction type. And so what we're looking at here is the wood anchored building stability criteria. So this assumes it's a wood frame house anchored to its foundation. And so it takes a decent amount of velocity before it could ever be washed away. Otherwise, only submergence could get these people. For this exercise, we're going to use the black line in the middle of this uncertainty band. So ignore the uncertainty. If Lyson will can't sample it, you don't have to. We're just going to look at the most likely. So I'll read this prompt. Flood severity is used to categorize the exposed population to high or low hazard. For detailed analysis, estimate the flood severity at each location where someone is exposed to flooding, whether it be on the road or structure. For purposes of this workshop, we will try to broadly categorize flood severity in terms of whether it is severe enough to wash away a typical wood building, or deep enough to drown able-bodied people in a typical one-story structure. So ignore the uncertainty. And obviously, we can't do this structure by structure like Lyson would. We're aggregating them all up to, your median or mode sort of case. So here's an example from a different project. You can kind of see what's typical here is, let's say, 6 feet of depth and 4 feet of velocity, feet per second. You go up to 4 and 6, and you're right around there. So a little below the line. So you would say, okay, if that was the median case, then they'd be fine. But it's kind of spread out in this area, and you can kind of recognize that. Some people get more and less velocity than others. So Paul here is estimating that about 30% of the people would be above the line and 70% would be below the line. Does that kind of track people? All right. So going back to our case, here's the depth. And again, you can hopefully see this in yours. And here's the velocity. It's transparent, so it's a little hard, I assume, even for you sometimes, but you can kind of flip into here and see, like, okay, let's ordinarily, again, Lyson is looking for the simultaneous depth times velocity, where it's going to look at max depth and max velocity. So given that, what do you think is the exposed or percent of the exposed population in the high hazard and the percent in the low hazard? So if you think everyone in Thunder Hollow is above that black line, you can say 100% of exposed population is high hazard. If you think no one in Sun City is, you can do the opposite. We're trying to estimate the percent that meet this criteria, both depth and their combination of max depth and velocity gets them above that black line in each of these 3 different reaches. That makes sense? I think this one has a lot more guesswork, in my opinion. So don't feel bad if you get different percentages in your neighbor in the same order of magnitude. So anyone just want a little bit more time? All right. How about let's run through Ample team. What did you get for percentage in the Thunder Hollow scenario? Say what? 100 and 0. Okay, sorry. For yeah, 100% are the high hazard and 0% in the low hazard. Gotcha. And 50-50. Yeah, so we look at this, you can kind of see kind of a mix of colors going on, right? And I don't know how clearly everything was printed. There's dots fairly well spread out. It seemed to be a little bit more concentrated down here at the bottom end of the reach where there's not as high depths. But I generally buy this sort of range, right? There's a lot of velocity going on here. So if you kind of assume, let's say 10 feet of depth and what were you guys thinking, like 4 to 6-ish velocity? It's like, so long as you get above, what is it, 5 at that? If you get above 5, it's like, okay, then you're going to be at the black line here, if I'm reading that right. If you assume everything's 4, then no matter what your depth is here, you're going to be to the left of the black line. And so this is where Lyson would sample uncertainty and put some of the structures in there depending on the iteration. But we're saying the black line is our metric. So you have to meet both depth and velocity. So in this case, that's like 5 or 6 feet per second is necessary to get in there. Okay, so somewhere between 50 and 100 or so for Thunder Hollow. How about Rumbling Springs? I guess this shouldn't really matter for if you're ample or minimum, sorry. So anyone from either team want to talk, because this is given you're exposed, where are you going to end up? So where are we in Rumbling Springs, you think? What percentage ended up in the high hazard? Sorry. 17? 50?
Yeah.
Yes, sorry. Any other numbers? Everyone's satisfied with that rough order, magnitude 10%? I think that's probably around where I did this. I did this a couple weeks ago. That makes sense. How about for Sun City? 1. I think I heard some zeros. I think I said 1 because it's like, there's some disabled people and other sort of stuff. That's not in the exercise. So Paul was like, no, you're wrong, because the depths have to be or maybe it's more the velocities. Nothing really gets you above that kind of 5-ish in there. So in a real study, I think it would be closer to 1. I think for this exercise, he wants to be a little closer to 0. Let's say 0 to 1-ish, right? There's going to be a small number of people in here because there just aren't the depths and velocities to get them into that high hazard. So the vast majority of people are going to be in that low hazard. All right, so we've gone through pretty much all the steps. The last thing is relatively simple, assuming you've got a calculator on you. Fatality rates for high hazard and low hazard are shown in the figure below. For the purposes of this workshop, we can apply the mean fatality rate for each zone and to the exposed population. For a more detailed estimate, you would sample each curve for a given evacuating group to determine fatality rate. So this is what we were talking about before, right? Lysen will sample each structure individually. Sometimes, all the occupants in the structure will die, sometimes 0, sometimes in between, if they're in that high hazard. For low hazard, almost always everyone will make it out okay, but there are rare cases where some or all people will perish. But using the averages, go ahead, apply your 71 and 0.0014 percentage points to your exposed population. See what life loss you get. Again, you take your exposed population, multiply it by the percentage in the high hazard zone, multiply that by the high hazard zone's fatality rate. Same for the low hazard. I was thinking at one point that I'd ask all of you for your life loss and then I'd make a histogram on the screen, but I don't think we got time for that. So instead, let's see. Total life loss. Did anyone end up in the 0 to 1 box? Seeing none. How about 1 to 10? 10 to 100. 100 to 1,000. Or so 1,000 to 10,000. All right. So we seem to have a little bit. How about 300 to 3,000? Almost everybody. So I think that's kind of what we're looking at here, right?